Hi, and welcome to this part 4 of our lesson 5 video that's all about bench work. And we're going to carry on by looking at taps and dies. And as you can see out front here, I lined up different types of taps. So let's take a closer look at those. Here we have a tap set, these three here. We have a taper, plug, and bottoming set of straight flute taps. Here we have another straight flute with a reduced shank. Here we have what looks to be a straight flute, but actually it's a spiral tip. Here we have a helical flute tap, and here we have a tap that has no flutes at all. And finally we have a taper tap for producing pipe threads. Now, of all these, this is the one that I can really say it has a reason to exist. It doesn't make or produce the same type of thread as all these other ones do, but these ones produce basically the same type of threads. So why so many? Let's start with this straight flute tap set, taper, plug, and bottoming. Now, what we notice looking closely at it here is the amount of taper on the end. Now we see that this taper tap has quite a pronounced taper, and it actually knocks off 9 to 10 and sometimes even 11 teeth off the end, from almost nothing to eventually a full tooth form. So this is quite a progressive taper. This plug tap is tapered on its end also, but has much less threads knocked off. So it goes from nothing to a full thread in about 5 turns of thread. And if we look at this bottoming thread, well, we notice that 1.5 to 2 threads are knocked off on the end only. So this goes from nothing to a full thread in less than 2 turns. Now, these taper taps, often called starter taps, are excellent for starting a tapped hole or a threaded hole. They are very progressively tapered on their tip, and that means that once inserted into the pre-drilled hole, well, they're ready to start cutting because they insert into the hole and cut very progressively. The first few turns of threads cut almost nothing, and then it progressively works its way up to a full thread 9, 10, or 11 turns later. So this actually reduces the cutting pressure because we're spreading that cut over several turns of thread. And also, it actually reduces the amount of wear on the tool. These starter taps last longer than the plug or the bottoming taps because more teeth are actually participating in that cutting action, and they're doing so in a very progressive way. Now, these taper taps are our go-to taps. They're the ones that we use unless we have to use something else. So, when can we use a taper tap? Well, when we're starting almost any hole, for one, and for finishing holes that are through holes that aren't very deep. Now, an example of that would be the holes that we threaded or tapped in the drill point gauge project. Now, for those holes, all we used were taper taps because we could form a full thread within the length of the tap, and we didn't have to bottom it out in the bottom of a hole. It was a through hole in a fairly thin part, 1/8 of an inch. So in those circumstances, well, these taper taps can be used to start and to finish a thread. Now, these plug taps have a smaller taper on the end, 5 threads knocked off as a general rule. And that means that they have a full thread that progresses quite a bit lower on the tool than it was the case with those starter or taper taps. And this means that this will produce a complete thread deeper into a hole than the taper tap would have. So what are these plug taps used for? Well, it's obvious. They're used to produce threads in deeper holes, threads that are too deep as far as depth of threading goes than our taper tap could have produced because of all the threads missing on the end. So taper, plug for a little deeper, and as we'll see in a minute, bottoming to go right to the end. Now these bottoming taps have almost no taper on them. They have a full thread right up to the very brink of the end of the tool, 1.5 to 2 turns max. And that means that they can get right down into the bottom of a hole and produce a full thread almost right down to the shoulder in the bottom of that hole. And that's what they're used for, getting the thread down there. But the question that's most often asked me when I say that is, why didn't we use this from the get-go? And the reason why we didn't, and that we went through the starter, intermediate, or plug, and finally the bottoming tap, well, is for 2 reasons. The first is, these are almost impossible to start into a hole that doesn't already have a thread in it. And if you've ever tried, you'll see it's quite frustrating. So the other taps are used to give something to get this one going into the hole, main reason. And the second reason, well, is mechanical. These tools cut, these bottoming taps cut on 1.5 to 2 threads on the end. All the other teeth are just there to follow along. And that means that those first few teeth will wear down quite quickly if we use them to cut the full length of threads all the time. They're really only used to finish that bottom hole because they wear down easily. And obviously it really puts a lot of strain on this tool if we pack all the punch of producing that thread on just the first 1.5 to 2 turns of this tool. So for those reasons, we really want to progress from taper to plug to bottoming whenever possible. And if we can finish a hole with the taper, well, we do it. If we need to use the taper and the plug, well, we do that. And we only use the bottoming when it's really, really necessary. What if the hole is too deep and I can't get to the bottom with this finishing or bottoming tap? Well, that's what the next type is for, and they're called reduce shank taps. So here we have our taper, plug, and our bottoming, and a 4th tap over here. Now this is one of another set. It can come in taper, plug, and bottoming, but as we see, it has a reduced shank. The shank is actually slightly smaller than the root diameter of its thread, and that gives this tap a great advantage. And that advantage is that these reduced shank taps can thread right through a part. In other words, the shank fits in the threaded hole that the teeth are producing without damaging anything. It clears the threads. So we can tap a lot deeper with a reduced shank tap. Again, the question comes up, why don't we always use these? Well, for 2 reasons. The reduced shank makes for a tap that's a lot more flexible, okay, so a little more difficult to control, and it makes for a tap that breaks a little easier, and that obviously is something we want to avoid. So again, reduced shank taps to be used only when required. The next tap in line here is a spiral tipped tap, and that is difficult to say. But if we look at its end, we'll see that we have 4 to 5 threads knocked off, so it is a tap that can be used to start a thread, and it has a straight flute, but it has a left-handed helical tip. Now, these spiral tipped taps have a nice straight flute on them, and at their tip, well, they have a left-hand helix that doesn't come all the way up the part. It really only covers a little more distance than the number of teeth that are knocked off or progressively knocked off on the end. And this left-handed helix angle, well, pushes chips in front of the tool. Now, if a right-handed spiraled tool pulls chips out of a hole, it's normal to think that a left-handed spiral will push chips ahead of the tool. And that is what we want to do here. So this is more of a production chip. Why? because we can produce through holes without having to stop, retract and clean the tool. We can cut, come out, cut, come out, going right to full depth each time, because the chips won't be clogging up my tool. They're being pushed ahead of the tool, and usually through gravity they can fall out the bottom. So these left-handed spiral tip taps are really more of a production type tool. The next one is this spiral flute tap. Now, if my helical tip tap was more for production, well, it could still be used for bench work because it had 4 to 5 teeth knocked off the end, so it can be engaged by hand. Well, this spiral flute tap has only 1.5 to 2 threads knocked off the end. We cannot use these taps for work on the bench, for bench work. These are strictly reserved for production and must be used on machines. Well, if the right-handed helix on a drill bit draws chips out of the hole, well, it's normal to think that a right-handed helix on a tap will draw chips out of the hole as well. And that's what these are used for, to get chips out of a hole by pulling them up out of the hole. So if the left hand spiral tip was for pushing tap or chips forward so that we could tap through holes easily, if we're giving ourselves the trouble to pull them out by the top, it's because these taps are made to tap holes that don't go through the part. And they are really reserved for production, because since they exit the chips through the top easily, well, they don't need to be backed off regularly and cleaned up like the straight flute taps do. They can barrel to full depth and barrel back out again. But great disadvantage, they are just about impossible to use at the bench for bench work. They are really reserved for machine applications. The last tap that we have here is also a pure production tap. It has no flutes. It's a forming tap. It doesn't cut a thread, it forms it. But it has to be used on a machine tool. You cannot use this tap by hand. Well, why would you want to form a thread instead of cut it? Well, in reality, for a home machinist, you're not going to want to form a thread. You're going to want to cut it, because forming threads is very touchy stuff, and it has to be done on powerful numerical control machines, NC machines, or on dedicated tapping machines. It's not something you can do by hand. Very touchy. Speed, lubrication, for each type of material, these things change. But it's still a good idea to understand why certain threads are formed instead of cut. When we talk about a good quality bolt, well, we know that those threads are rolled on. That's not cut, that's rolled. It's a forming operation. And in the case of high quality nuts, internal threads, well, they can be formed with forming taps. And why? Well, it's a question of grain structure. And here we have a really excellent representation of the grain structure in red in a piece of a bar of steel and a thread that has been cut. And we notice that I have cut the grain. The grain structure stops and starts and stops and starts. This is not the best situation for strength. If I compress the material to form the thread instead of cutting it, well, I maintain the structure of the grains. I just compress them and deform them, but they stay there, and I get a much stronger grain structure. So formed or rolled threads are stronger than cut threads, and that's why they exist. So let's recapitulate. I have a tap set of 3 taps, taper, plug, and bottoming. Standard set here that is strictly reserved for bench work. They do not clear chips properly, so they have to be backed off regularly and cleaned, because the chips will clog those straight flutes. Then we have another hand tap, or tap to be used for bench work, which is a straight flute but reduced shank. Over here we have our spiral tip, which can be used for bench work or can be used for production work. It's really half and half, and it pushes the chip ahead of the tool. Here we have 2 really production tools, a helical flute, and a forming tap that are really used with machine tools to produce threads. And at the end here, well, we have our pipe thread that I'm really not going to be covering in this video. And that brings us to tap wrenches. Now, this is the standard tap wrench, the type that we see most often, and it comes in all sizes. This is a medium size one. We have a lot smaller one here, and they're meant to drive the square tang on the end of the tap. These are the preferred tap handles, and we'll see why in a minute. Here is what's called a T-tap handle, and it's generally used for chasing threads, and that means repassing or passing a tap through a finished thread to get rid of burrs or damage. Generally not suggested for tapping holes, it's more for chasing, and like I say, we'll see in a few minutes why. So let's start with these T-handled tap holders. And I mentioned that they're generally, or I suggest to use them for chasing threads, and that we should avoid using them for tapping threads. And why? Well, because they have a certain height to them. Once the tap is inserted, we've actually lengthened the tap quite a bit. And that creates a problem. When we turn the tool, there's always going to be a little flexion on my force. Okay, and the higher that we are, the more chance that I have of breaking the tap in the hole. And that's one of the reasons. And the second is the shortness of the handle on them. The longer the handle, the more feedback the tool is going to give us, because the less we have to force on the handle to actually turn the tap. When we can force quite little or delicately, well, our fingers really give us a lot of information about what's happening on the level of the tap. We can actually, when we have long handles, feel the tap flexing. And you get to know when too much is too much before it happens and you break the tap. Whereas these stout, short handles with high sets, well, they don't give a lot of feedback. They're hard to get information from, and we tend to over torque and break our taps. One last thing, that is that we often are tempted to hold these with one hand, and obviously our wrists aren't ball joints, and we can't turn perfectly symmetrical to our axis, and that means that as we turn, we pull at the same time. This is the normal movement. And that obviously puts adverse force on the tap and will or could break it. So really not used in general, used when we have to. But these T-handle wrenches are really practical in two types of situations. When we have reduced access, and this a smaller version of the tap wrench is easier to get into certain places, and the other is if our tap doesn't have a center hole on its tang, and we need one, because this one doesn't, but some T-wrenches have center holes on the end, and that means that when a tap is in this T-wrench, I can use a spring-loaded center to align the tap in the hole, and that's really practical. So let's go take a look at how this setup can work. So I want to tap a 1/4-20 thread, so I've chosen a 201 thousandths of an inch drill, and I've pre-drilled a hole in this block of mild steel. And we can see that the block is clamped to the table and that the table is locked in place, because for this operation to work, I have to maintain the alignment of the drill and the hole until my thread is well underway. And we can see here that we're still lined up. And we can see that I've given myself a lot of room here, because what I'm going to do now is I'm going to remove this drill, I'm going to replace the drill with this spring-loaded center, and I'm going to use this to guide my 1/4-20 tap into the hole straight with my center hole in the T-handle. So let's set this up. Now we can see that this is quite practical because I can turn forward and back up, and since I'm spring loaded here, well, I can go both ways and I can tap through. But we can also see that this is quite awkward. This is a very small handle and it's not easy to work with. So since I'm well engaged into the part, now would be a good time to retract and remove this setup and bring my part and my tap over to the bench vise and finish this job with a proper tap handle. So let's say you don't own a T-handle with a center hole in it, and you don't have one of those spring-loaded centers to guide your tool. Well, you can still use your drill press to guide your tool straight into your hole. And for that, well, we have our part with our pre-drilled hole, 201 thou for quarter 20. I have my starter tap, or my taper tap, that I'm going to install into my drill chuck and snug down, but I don't want to kill it. Just good and snug, but not murderously tight, okay? Because if it's going to slip, I'd rather it slip here than break. Now, this is not a good situation. We shouldn't use power when we're doing this, at least not at the start. And if you do, well, you do it at your own risk. But we can still use the alignment without using the power. And here's how. And first off, we want to make sure we don't start the machine. So let's unplug it. I mean, these little removable switches are nice, but unplugged is definitely not going to start. So my machine is unplugged. I'm going to, and I've left a lot of room here, and you'll see why in a few minutes. I'm going to bring my tool down to my hole and engage it. Note that I'm maintaining a light pressure here, but as I turn the tool into the part, this continues on its downward movement. Now, my tool is engaged by 2.5, 3 turns, and that's about what I want here for it to be stable and straight and well engaged. I do not let up on the pressure here. Light pressure continues to bear down. If I let go of this, the spring-loaded handle is going to draw my vise up and probably break my tap. So I maintain a light pressure, and I keep my key close at hand, and I loosen the chuck, and now I can come right up. And that's why I left myself a lot of room here. Now I can work, and I can complete the tapping operation with a proper handle. But this isn't the right place to do it. This is a floating vise and it isn't stable. So what am I going to do? I'm going to remove my part from my vise. I'm well engaged, good and straight. Head over to my bench vise, my stable third hand, and there I'll complete this using the proper tap handle. Now, what we have here is a tapping head, and it's definitely not something that you're going to want in your home shop. It really is a production tool for tapping many holes in a part, or many holes in many parts. it really accelerates production. Now, why am I showing it? Well, it's good to be exposed to different things. Now, remember, if you expose yourself in public, well, you're going to get arrested, and that's not a good thing to do. But it's good to get exposed to new things. So even if this isn't a home shop tool or for beginners, well, it's still nice to know that it exists. So let's start at the bottom here. I have my part that isn't fixed to the table, it's floating, and that way I'll be able to move from one hole to the next quickly. And I put it in a vise so that I have some mass that will counteract the force of the tapping. So I have pre-drilled 5 holes, and they are not through holes. Since they don't go through the part, I'm going to be using, for a production tap, my spiral flute tap that's going to pull the chips upwards and clear them out of that hole. Next we take a look at my tap itself. It's a helical flute tap, and it's mounted in the tap holder of the tapping head. That is a floating tapping holder. If I can see, there is some movement sideways, up and down. It's not perfectly fixed in there, and it is spring loaded. Now this tapping head does 3 things. It gives me that floating action that permits me to tap with power, so the machine will align and rotate this tool into the part. Because it's floating, it gives me a little leeway here. But it also has a reversing action to it. So this will feed down into the part, and once I change direction, once I pull up on the spindle, this tap will change directions of rotation and will spin out of the hole. So it can spin down, it floats, it has a reverse. And it also, and this is important, has a viscous clutch. Now this clutch will apply a certain amount of force on the tap. And if I exceed that force, well, it's just going to spin, okay, or slide. And that's going to save me from breaking my taps. And I've already set this clutch at a level 2 for my 1/4 inch 20 tap that I'm going to be using. And finally, well not finally, but almost finally, we have this arm. If I want the planetary gears and the reversing action to work, I have to block the rotation of at least part of the gear train. And that's what this arm does against this stop. But it still has to be free to move. And that's why it just leans up here, and it can still float up and down freely. And finally though, we're going to be using tapping oil to help with the tapping action and the cutting action here. So let's take a look at what this looks like when it's actually cutting. Well, that was fun to see, and like I said, it's not a tool that we're going to use or that we would use in a home shop, or it's not a beginner's type tool, but it's nice to know that it does exist and to see how it works. And for us here, it's important to mention that there are at least 2 other methods, and the 2 most popular methods for starting taps straight into parts, well, we haven't mentioned in this video because they're part of our practical video series, and that is using a tapping block or a pre-drilled clearance hole in a square block that we can use to align a tap, and we see that in our 1, 2, 3 block video, and here's a link for that. And there's obviously the tried and true technique of using the square to align the tap, and we can see that also in our 1, 2, 3 vlog video with that same link, or in our drill point gauge video. So take a look at those to get to know those basic techniques. Now would probably be a good time to start adding links for other notions that are coming up. like millwork that we're going to be getting into more and more with our projects. So this would probably be a good time to look at the vise alignment, or aligning a vise or tramming a vise, depending on how you want to say it. And here's a link for that video, and also on a video on how to square up a block in different types of situations, So here is a link to my squaring up of blocks on the mill video. So I think that'll keep us busy for a while, and until I complete the part 5 of this lesson 5, well, have fun, be safe, and happy machining. But what if the hole is too deep and I can't get to the bottom with this plug or bottoming tap? But what if the hole is too deep and I can't get to the bottom with my finishing tap, taper plug and bottoming? I'm going to get this. What if the hole is too deep?
You